Alright folks, welcome to video tutorial number 2. This is unit 3. Today we'll be covering correlation using SPSS and writing about that. This should give you a chance to become more familiar with working with SPSS, as well as give you an opportunity to spend some time thinking and writing about the role of statistics in your life in the second half of the exercise for this unit. So by the time you're through with the SPSS portion of this, you should be able to test a bivariate correlation. It's a correlation between two variables if you're up on the vocabulary. And you should also be able to write about it in a fairly coherent way. And as we go, I'll provide you with some model language with which you can do that. And you should feel free to copy that in any way you like. Use that freely. It's not plagiarism. It's the recommended format from the APA, which is the accepted format in the social sciences. So before we get started on the SPSS exercise, though, I want to cover a few words about correlation, maybe clarify some points from the reading that you've done up to this point, and make sure that everybody going forward knows what we're looking at when we say correlation. So, correlation simply is a way of measuring the strength of a linear association between two variables. So the object of correlations is to test for linear association between two variables. Of course, when we say linear association, we mean that there's a link, an association, a relationship between the two variables in question that takes on, at least to some extent, the form of a line. And the stronger that linear association, the more line-like that relationship is. So when we have a linear association, we say that one variable increases or decreases in value as the value of the other variable increases or decreases. And we'll talk about the character of these relationships in a minute. And the correlation measure that we use, specifically Pearson's R, although there are other correlation measures, for instance Spearman's rho, that are in use out there, Pearson's R is by far the most widely used correlation measure, and certainly the one we will be using throughout the course of the statistics class. So linear association, or covariation among two variables along a straight line, is what we're talking about here. And the values, we have to keep in mind, change in proportion to one another, meaning as one goes up a certain number of units, the other one consistently goes up a certain number of units in its predicted value. Now, linear association can be positive or negative. So in the case where we have an increase in x with a proportional increase in y, we say that that is a positive linear association. And the line slopes up when we look at the scatter plot. If we were to superimpose the regression line over the scatter plot, we'd see that the line goes from the bottom left, as you're looking at it, to the upper right, both increasing in proportion to one another. In the other case, where the value of x increases and we see a proportional decrease in y, we'd see a negative linear association in which the line slopes down, beginning on the upper left and moving to the lower right of our bivariate scatter plot. I want to caution you at this point and say that the absence of a linear association does not mean that the variables are unrelated. They could be related in many different ways. For instance, they could be curvilinear or quadratic in their form, meaning that it's an arc or a parabola or some other curvy, wavy line that has nothing to do with a straight linear association. But the measures we're studying and the type of relationship we're interested in here are predictably linear and proportional in their value. So it's the simplest form and probably the most useful form for our purposes. So these are examples of linear association. On the left, as you're looking at the screen, is a linear association between happiness and income. On the right, there's a linear association between happiness and income. And as you can see, they're very different. On the left, we see a sort of loose, amorphous cloud from the first group of respondents. And on the second, we see a much more tightly organized, cigar-shaped, very clearly linear relationship. Both of these, to some degree, have some positive linear association, meaning that the relationships start in the lower left and climb in value proportionately with both variables moving to the upper right. So the direction of the relationship is the same, but the strength of the relationship is very different. As you can see, as I pointed out a moment ago, the relationship in the second graph, the one on the right, is much more tightly bound into a line, and that would show a higher degree of linear association. And when we come to the measurement tool we'll be using, we'll talk a little bit more about this strength of association. So let's move on to it. So how do we measure linear association? Well, linear association in our particular case, and in most cases, is measured by the correlation coefficient, or R, or formally Pearson's correlation coefficient. Generally, you'll just hear people say R, or Pearson's R. So R can range in value from -1 to 1. -1 passing through 0 to +1. And in the case where we have a +1, it indicates perfect positive linear association. That means that all points fall exactly along a single line, and that line goes from the lower left to the upper right of the scatter plot. -1 indicates perfect negative linear association. And in that case, the line goes from the upper left to the lower right of the scatter plot, with all of the points falling perfectly on a line. Now, perfection is not a good thing in this case. Perfection means that you've probably measured the same thing twice. For instance, you've measured height in inches and height in centimeters, two different numbers, but with the exact same proportional value. Measuring the same thing, just using different units. Generally, when we look at Pearson's R and get a 1 or a -1, we know we've screwed up in some way. We've picked two variables that are obviously the same. Now, that doesn't mean a higher linear association is always bad. When we're in the range of 0.95, 0.85, 0.75, or even anything generally above 0.25, and we'll get back to that in a minute, we say there's linear association. We get up around 0.75, we make claims about strong linear association, or obvious and clear linear association. Right? But let's keep in mind here that R is determined, the Pearson's correlation coefficient is determined by how close the points fall to an exact line, not the slope or the steepness of the line. Some people get confused by that. I don't want you to be one of those folks. Right? It doesn't matter if the line is climbing fast or the line is climbing slow. It's not a measure, the climb is not a measure, the slope is not a measure of the strength, it's a measure of the proportion between the units of the two variables. So remember, the strength of R is determined by how close those points fall to the straight line. So, some additional points here to keep in mind. As a rule of thumb, R of 0.25 is considered evidence of a linear association, evidence of a linear relationship. It's desirable to have interval or ratio level data, as we also like to have normal distribution of that data. For our purposes, the variables I've given you in the data set are all ratio level, They're all normally distributed, so you don't have to worry about that. Feel free to mess about with them in any way you like. A last note, it's important to remember that correlation does not imply causation. That is to say, just because two things have a relationship and go together doesn't mean one thing is causing the other. They just may go hand in hand. All right, well, with that, let's move on to actually working on the assignment. Why don't we go ahead and make sure you have a copy available of both the Unit 3 data and the unit instructions where you can see them. You can get them either in the assignment section on Canvas or in the unit instructions in the files section on Canvas. And once you have those open, we'll get started. So as you can see, I have here before me the data set from Unit 3. And in this data set, we've got 32 variables of various types, all ratio level, all taken from the GSS, the General Social Survey, from the North American Opinion Research Center at the University of Chicago, which is their annual series of surveys in which they ask folks about their lives and social issues and opinions and all kinds of great stuff. A very rich source of data. I've actually reduced the full data set to about, as I said, 32 variables and about 673 cases. I made it a very clean, very easy to use data set, so you wouldn't have to struggle finding the things you needed and getting things done. So let's switch from the data view, which we're in, to the variable view, and you can do it down here, the bottom of the screen, where I'm circling around. You can see we have a number of different types of variables here. Of course, as always, we have a case identification number. In this case, the numbers are not all sequential. They're broken up because I eliminated many cases with missing data. So you would have a very clean data set to work with. But other than case ID, we've also got things like the respondent's income in constant dollars, the highest year of school completed, the number of brothers and sisters, days of poor physical health in the past 30 days. And these particular variables here at the top of the list, with the exception of respondent's income, are the ones I'll use in my examples, and I put them right there at the top of the list so you could easily find them. Now, beyond that, we have all kinds of information about their personal habits, about their work life, and you can read through these case labels on your own, and for purposes of the assignment, you'll need to find some variables you're interested in and think maybe there's a relationship between them, and you can check out that relationship for yourself as part of the assignment. But for our purposes, in giving the examples, I put the stuff we need right at the top of the list. Let's switch back to the data view, and you can get some idea of what the data looks like. You can see all numbers, all meaningful in as much as they are actual numbers that you can do math with. Very useful for those purposes. All right, so let's begin on step 2 of the SPSS portion of the unit exercise. And here it says to create a scatter plot and a bivariate correlation for the variables real inc, which is real income in constant dollars, and educ, which is years of formal education. So let's try that one out. If you'll remember from last time, we make the scatter plot by going to Graphs, using Chart Builder, choosing Scatter or Dot, the simple one, and then dragging real income in dollars and educ into those boxes and hitting OK. And we get our scatter plot. And what do we see? Well, we see some outliers, right? Up here are those people who make much more money than the average folks, and lots of folks clustered down here. Predictable clustering around high school and some college, right? Now, question here, is there enough of a linear relationship here? And there looks to be some linearity, not very strong, but some linearity here. Is there enough to say this is a significant linear association? So how do we do that? Well, switching back to SPSS, away from the output and back to the program itself, we can do this by finding the Pearson's correlation coefficient and interpreting it. So let's do that. Let's do this one right now. Go to Analyze, Correlate, Bivariate. Analyze, Correlate, Bivariate. Open that up. As you can see, I've already been playing with this, so I know how it turns out. If you want to change from, by the way, if you want to change from displaying the variable names to displaying the variable labels, it's easy to do. Just right-click in this box, and it'll give you the option of switching back and forth. Since I'm using the variable labels instead of their, the variable names instead of their full labels, I'd suggest switching to that. It'll make your life a little bit easier. So here we want to look at real income and education. Want to make sure we have Pearson's correlation checked off. It's the default one, and it's a two-tailed test, so make sure you do that. You want it to flag significant correlations. It means it'll give you little asterisks next to the ones that are meaningful, which is handy if you're trying to spot them out. So once you've got those in the box, go ahead and hit OK, and let's look at the results. Yeah, there we go. Now, what are we interested in looking at here? Couple of pieces of information worth noting. Of course, you have the variable names across the top and along the side. Now, of course, real income in constant dollars and real income in constant dollars should be perfectly correlated in this correlation matrix because they're the same thing. We're ignoring that. We're not interested in that. What we're interested in is the relationship between real income in constant dollars and the highest year of school completed. Right? Basically asking the question, will we see a boost in income as we see a boost in education? Well, what do we see? Well, two pieces of information we're looking for here, in this cell or in this cell, which are the same results, just reversed for the variables. So let's look here. We have two pieces of information. The first is the Pearson correlation coefficient of 0.305. Now, what was our rule of thumb for what's a meaningful correlation? It's 0.25. This one is 0.30. Got something going on here. Now, is it a statistically significant correlation? A test of statistical significance in this case is to find out whether or not we have an alpha level or a p-value, which is another name for it. You may hear alpha level, you may hear p-value, you may hear two-tailed significance, which is what it says in this case. But basically, these are all the same. All these things are the same. And what they mean is, what's the percentage chance of a false positive result? Right? What's the percentage chance of reaching this result in error, thinking that you got a good and meaningful result, and it's really just garbage? Well, in this particular case, the p-value, the two-tailed significance, is 0.000. Now that's SPSS's way of cutting it off when it's very certain. It's what we call a truncated result. In this particular case, 0.000, the highest that could be is 0.0009, right? Which is way, way, way smaller than our acceptable chance of being wrong, which is 0.05. And this measure of 0.05 is very standard across all the tests we use. It essentially says we have room to say a 5% chance of a false positive result is acceptable to us. Another way of saying that would be, we're 95% certain we've arrived at this answer correctly, so we're going to accept it. Now, 95% seems like a fairly arbitrary cutoff, but it's the one that's most often used. Occasionally we'll see 0.10 or a 90% chance, but almost always 0.95. So, in this particular case, of course, we've got 0.30 for the Pearson correlation coefficient and a truncated result at 0.000, saying that we have a statistically significant relationship here. We have a statistically significant linear association. So this is a good one. This is one where there is a linear association and there is some predictive value here. It's not perfect. It's not acceptably close to perfect where we might like it, but there is something going on here. There is some relationship between how much school you have and how much money you make. Right? The more school you have, the more money you make, up to a point. Now, if you'll look at the unit instructions, I also included the language for interpretation for this particular one. You'll see it under the label Model Language for Steps 2 and 3. So here, what we're interested in reporting is the correlation coefficient and the p-value. Now remember, as I said just a few seconds ago, p-value, statistical significance, the two-tailed sig right here, and alpha level are all talking about the same thing. When you hear those terms, what we're talking about is the chance that we've arrived at a false positive result, right? So we want to report the Pearson correlation coefficient, and we want to report the two-tailed significance. And if you look at the language that I've included, it reads like this. There was a significant correlation between the respondent's income in constant dollars and highest year of school completed. And it reports R at 0.305 and P at 0.000. Or you could put P less than 0.05. That's also acceptable, but it's generally just easier to include the exact number rather than the other. All right, so that's the first one. That's the first example from step 2. Let's try the second example from step 3. And I do want to see you hand in these examples to make sure you did them. You don't just rush on to the other work. So please don't X out. Don't get rid of the output yet. Just move back to the SPSS window. And let's try the next one. So the next one in step 3 is to create a scatter plot and a bivariate correlation for the variable SIBS, or the number of brothers and sisters of the respondent, and phys health, which is a little more complicated variable. It's actually the number of days of poor health reported by that person in the previous 30 days before responding to the survey. So we want to find out, is there a correlation between the number of siblings you have and feeling sick in the last month? Right? So let's do the graph first. Chart builder. Okay. We can just drag those back that we had before and find the number of brothers and sisters and days of poor health, right? Or, as I said before, SIBS and phys health. Once you've got those in the boxes, we'll go ahead and hit OK. So what do we get? Looks lumpy on the ends, doesn't it? Not much going on here. Doesn't look too linear at all. All right, but rather than just using the eyeball, let's use the math. Let's figure it out. So, skipping back to the data editor, let's do the bivariate correlation. Analyze, correlate, bivariate. Clear out our box and find SIBS and physical health. Once again, make sure that Pearson's, two-tailed, and flag significant correlations are all checked off. and hit OK. So what do we see here? Nada, right? Pearson's correlation coefficient well below 0.25, which is our sort of rule of thumb we talked about. The two-tailed significance is 0.49. Remember, we're looking for something that's lower than 0.05. We say that again, lower than 0.05, not 0.5. This is way above. So this one, there's no linear relationship between these two things. And you can see that. I mean, it's, it's got a little lump here at the end, a little lump there, slightly bimodal looking. Maybe there's some sort of weak curvilinear relationship. But really, it's either you're not sick or you're very ill, and it doesn't have much at all to do with your number of siblings. So, how do we report that one? Well, if you take a look over at the model language on your unit instructions that you should have open, you'll see that since this is not significant, we just change the language a very little bit. We say there was no significant correlation between the respondent's number of siblings and the number of days of poor physical health in the last 30 days. R equals 0.027, P equals 0.49. Period. And that's it. That's how you do them. That's how you interpret them. Pretty simple. Pretty simple. All right. Now, here's your chance to do some on your own. I've included a whole bunch of other variables that you can use and try and figure out if there's a correlation between these variables. I suggest you begin by thinking about the relationships that might exist. So let's look back in the variable view and think about some of the possible relationships, right? Education and poor mental health, maybe schools driving you crazy, respondents' income and family income. I've got to guess those are pretty closely correlated. There's all kinds of stuff going on here. But if you pick through these labels, if you look through these labels, theorize a little bit, hypothesize a little bit about what might be related. I mean, we've got things like height and weight, definitely going to be related, right? How much time you have for leisure, how much time you work, all kinds of stuff you could theorize about here. And feel free to rip off any number of ones I just said if you feel you can't make up any of your own. All right, so give those a shot. Make sure that you save it all in your SPSS output along with the two examples we did together. Write out your interpretations in an MS Word document and hand in both the SPSS output and the MS Word document. Also, don't forget there's a second part to this week's assignment, and that's a little bit of essay writing, once again reflecting on the role of statistics in your life, not just in your education, but in how you lead your day-to-day life. So make sure you check out at the bottom of the unit instructions, or at the bottom of the assignment section in Canvas, there's a writing section for Unit 3, and it asks you to watch some video and then write a 450 to 500 word essay that reflects on what you've seen and reflects on how you live. So check out the writing prompt. Make sure when you're done with that essay, you also hand that third document into Canvas. You'll have 2 MS Word documents and some SPSS output. All right. I guess that does it for today. As always, if you have any questions, please let me know. I'm available by discussion board and email. Be glad to answer anything I can. Good luck.